Welcome to the Deep Dive, your direct shortcut to truly understanding crucial machine learning concepts. Perfect for anyone looking to quickly get up to speed.
Yeah, get well informed quickly.
Exactly. Today, we're diving deep into two fundamental classification algorithms, logistic regression and support vector machines, SVMs.
Two big ones.
And then, maybe even more importantly, we're tackling how we strategically split our data for training, validation, and testing. It sounds basic, but it's foundational.
It really is. Often underestimated, I think.
Our mission today is for you to move beyond just the definitions, really grasp how these tools work, when you use each one, and, crucially, why data splitting is sort of the silent hero behind models you can actually trust.
That's a great way to put it. And
I-
it's vital to see how these things connect, right?
Mm,
The algorithm choice and how you handle your data,
yeah.
they're totally linked. You can't really succeed without understanding both.
Spot on. Okay, let's unpack this. We'll start with logistic regression. Now, here's something that always trips people up right away, the name. Despite having regression right there in the name, it's actually used for classification. That seems really counterintuitive, doesn't it? Why call it that?
That's a great point. And yeah, it does confuse people. The regression part actually comes from its core mechanism. See, it models the probability of an outcome.
Okay, probability, like a percentage chance.
Exactly, a value between 0 and 1. And modeling that continuous probability feels like a regression task. But then, and here's the key part, it uses a threshold, usually 0.5, to turn that probability into a definite class label, like yes or no.
Ah, I see. So the method has a regression field, but the final output, the goal, is classification.
Precisely. So at its heart, logistic regression answers, what's the probability this thing belongs to class A or class B?
Makes sense. And you can think of simple examples, right? Like, is this email spam or not spam?
Or will this customer buy the product or not? Classic binary questions.
But it gives you that probability layer first.
Which is often super valuable for business decisions. You don't just get a yes, no, you get a how likely. So you can prioritize, maybe focus on customers who are, say, 90% likely to churn versus only 60% likely.
Right. That nuance is key. Let's maybe visualize it. Say we're predicting if someone buys a product based on age. We have some data. Maybe a 20-year-old and a 25-year-old didn't buy.
Okay, so that's a 0.
Right. But then a 30-year-old and a 35-year-old did buy.
That's a re.
Okay, so logistic regression doesn't just draw a hard line. Instead, it fits this S-shaped curve.
The sigmoid function.
Right, the sigmoid. And that maps the age to the probability of buying. So for someone who's, 28 years old, the model might output, there's a 67% chance they'll buy.
And then the threshold kicks in. If it's over 0.5,
It classifies as yes, purchased. If it's under 0.5, it's no.
and that sigmoid function is mathematically neat because it squashes any number, really big or really small, into that nice 0-1 probability range.
Yeah.
Makes the output always interpretable as a likelihood.
So when is logistic regression the obvious choice? I guess, number one, when you actually need those probabilities.
Absolutely. If the probability itself is valuable information.
And for straightforward binary classification, yes-no type problems.
It's often a great starting point there. Simple, efficient.
And this seems important. When you need a model that's highly interpretable, you want to know why it made a prediction.
That's a huge plus for logistic regression. Because of how it works, you can look at the coefficients for each feature, like age in our example, and directly understand its impact on the odds of the outcome. It's not a black box.
You can quantify how much a change in age shifts the probability. That's really valuable, especially in fields like finance or healthcare, where you need transparency.
Definitely. Okay, so that's logistic regression, focused on probabilities. But what if your main goal isn't the probability itself, but finding the absolute best dividing line between your data points?
Ah, okay. The different approach.
Yeah, this is where support vector machines, SVMs, come in. They have a very different philosophy. The core question for SVM is more like, where can I draw the boundary line that creates the widest possible street or margin between the two classes?
Widest margin. Okay,
Wow.
so it's focused on the separation.
Exactly. It's obsessed with that boundary, the hyperplane. It wants to maximize the gap between the two groups of data points.
So if I picture like blue dots and red dots on a chart,
Yeah.
SVM tries to find the line that separates them, but not just any line. It wants the one where the empty space between the closest blue dot and the closest red dot is as wide as possible.
You've got it. And those closest dots, the ones right on the edge of that margin, those are the support vectors. They're the critical points that define the boundary.
Hence the name support vector machine.
Makes sense, right? It's finding the line that cuts between those two clouds of points with the biggest possible buffer zone.
You mentioned it can handle complex stuff too, not just straight lines.
Oh yeah, that's where it gets really powerful. It can use something called the kernel trick. Imagine your data is all mixed up in 2D, and you can't draw a straight line to separate it.
Okay, like a swirl pattern.
Kind of like that. The kernel trick lets SVM mathematically find a separating boundary, as if the data was projected into a higher dimension, like 3D, where maybe a simple flat plane could separate it.
Whoa. So it finds complex, curvy boundaries without actually doing all the heavy computation of moving to higher dimensions.
Exactly. It's a very clever mathematical shortcut. Makes it great for nonlinear problems.
So when you reach for SVM, it sounds like it's good when your data has a pretty clear separation, even if it's complex.
Yes, if there's a reasonable margin to be found,
And when you really need high accuracy.
often, yes, it can be very accurate.
And maybe for small to medium data sets. You mentioned something about speed later.
Good point. It works well there. And definitely when you need to separate nonlinear data using those kernel tricks we talked about.
But the trade-off for that cleverness with kernels is interpretability, right? It's harder to explain why SVM made a certain prediction compared to logistic regression.
That's generally true, yeah. It's more of a black box in that sense.
Okay, let's put them head to head then. A quick comparison. Type. Logistic regression is probabilistic.
Gives you probabilities. SVM is geometric.
Focuses on that margin, the hyperplane. Okay, output. Logistic regression gives probability plus class, like 72% chance of default, so yes, default.
Whereas SVM typically just gives the class yes or no. Less nuance there, usually.
Handling nonlinear data. Logistic regression often needs you to manually create new features, which can be work.
Yeah, you might need to add polynomial terms or interactions yourself. SVM uses kernels.
Much easier for nonlinear stuff, typically. Interpretability,
Yeah.
logistic regression is generally quite clear.
Very interpretable. SVM, not so much.
Less interpretable. And speed. Logistic regression is usually fast, scales well.
Yep. SVM can get slow, especially on really large data sets. That kernel computation can be intensive.
Got it. So that bank loan example really highlights the output difference. Logistic regression. 72% chance they'll default.
SVM, just yes, default. The Y is harder to get from the SVM.
Yeah.
Might be fine, might not. Depends what you need.
Excellent comparison. Okay, we've got these two tools. Now let's shift gears to something absolutely essential no matter which model you choose, how you handle your data. Specifically, data splitting.
Yes, the unsung hero.
Mm-hmm.
Seriously, you can have the best algorithm in the world, but if you mess up your data splitting, your results can be completely misleading.
Why is it so important? Well, supervised models learn from labeled data, right? But the whole point is to know if they work on new data they haven't seen before.
That's the real test.
Think about a spam filter that looks great on old emails but misses all the new spam tactics.
Oh.
Or a house price model that seems accurate on the houses it learned from but is way off for new listings.
Total disaster in practice.
So you absolutely cannot just train your model on all your data and call it a day. That leads to overfitting.
Overfitting. The classic problem. The model basically just memorizes the training data, noise and all.
Like cramming for a test by memorizing answers without understanding the concepts.
Exactly like that. It aces the practice questions it saw, but fails miserably on the actual exam with slightly different questions. An overfit model looks great on training data, but is useless in the real world.
Okay, so to avoid this, before we even start training, we split our data, usually into 3 distinct piles: training, validation, and test.
The three amigos of data splitting.
First up, the training set. This is the biggest chunk, maybe 70% of your data. If you have 1,000 rows, it's about 700. This is where the model actually learns its patterns, it fits the line, adjusts its weights, does its homework.
This is the classroom where the algorithm does the learning.
Then the validation set, maybe the next 15%. This one's used during the development process. You use it to see how well your model is doing and, importantly, to tune it.
Right. It helps you make choices.
Like, which model should I use? Logistic regression, or maybe a random forest? Or tuning those hyperparameters things like the learning rate, or how complex a decision tree is allowed to get.
So if you're trying different K values in K nearest neighbors, you'd see which K performs best on the validation set.
Exactly. And you'd measure performance using things like accuracy, precision, recall, F1 score on this validation data.
It's your feedback loop during development, helps you iterate and improve without touching the final test set, crucial for tuning and model selection.
And finally, the test set, or holdout set. The last 15%, this one is sacred.
Absolutely. Handle with care.
You use it only once, right at the very end, after all training and tuning is completely finished. It gives you your final, unbiased estimate of how the model will likely perform in the real world.
The key rule: the model has never seen this test data during training or validation tuning. Never.
It's the final exam, the ultimate reality check.
Your most honest performance estimate.
So that 701-515 split is common. Let's walk through the process flow. 1. Train the model on your training data. X-train, X-train.
Got it.
2. Make predictions on your validation data. X-val. Compare those predictions to the actual eval. Calculate metrics.
Check how it's doing.
3. Based on those validation metrics, you might go back, tweak the model, change hyperparameters, maybe even try a different algorithm altogether. You repeat steps 1 and 2.
Right. Iterate until you're happy with the validation performance.
4. Once you are satisfied, you finalize your model. No more tuning. Then, and only then, you unleash it on the test set, X-test. Make predictions, compare to E-dust, calculate final metrics.
And that final score on the test set is your reported performance, your best estimate of real-world generalization.
And getting the balance right is key. Too little training data, the model doesn't learn well. Too little validation or test data, your performance estimates aren't reliable.
It's a balancing act, for sure. That iterative train-validate cycle helps find the sweet spot before the final test.
Let's take that customer churn example. 10,000 customers. You might split. 7,000 for training the churn model.
Okay, the main learning chunk.
Then 1,500 for validation. Trying different model settings, maybe comparing logistic regression versus SVM for churn prediction.
Tuning and selecting based on those 1,500.
And the final 1,500 are held back as the test set. Once you've picked your best model and settings based on validation, you test it on these last 1,500 for the final performance number.
And in Python, using sklearn, you'd often use train to split twice to achieve this. First, split off the test set, then split the remainder into train and validation.
Exactly. So the real-world steps are clear. Split of, train, lib, and validate, to choose tune, of test, once at the very end.
That discipline process is just fundamental. It builds confidence that your model isn't just memorizing, but actually generalizing.
Okay, but what happens if your data set is really small? Say only 300 rows total.
Yeah, that's a common challenge.
That 701-515 split suddenly looks pretty scary. You'd have maybe 210 for training, but only 45 for validation and 45 for testing.
Those validation and test sets are tiny. Any metrics you calculate on just 45 examples could be wildly unreliable. Just random chance could make one model look much better than another. Plus, you have less data for training, too.
This is where n-fold cross-validation comes to the rescue, right? It's a much smarter way to handle small data sets.
Absolutely. It's your best friend when data is scarce. Let's use 5-fold as the common example.
Okay, 5-fold cross-validation. How does that work?
You take your entire data set, let's use those 300 rows, and you divide it into 5 equal chunks, or folds. So 60 rows per fold.
Okay, 5 groups of 60.
Now, you run the training and validation process 5 times. In the first run, you train the model on folds 1, 2, 3, and 4. That's 240 rows.
And validate it on fold 5, the remaining 60.
Exactly. Then in the second run, you train on folds 1, 2, 3, and 5.
And validate on fold 4.
You keep rotating which fold is used for validation. Train on 4 folds, validate on 1. You do this 5 times in total.
So by the end, every single data point has been used for validation exactly once and for training 4 times.
Precisely. You get 5 different validation scores, like 5 accuracy scores. Then you average those scores.
Okay. So averaging the 5 scores gives you a much more stable, reliable estimate of the model's performance than just using one tiny 45-row validation set.
Way more reliable. It maximizes the use of your limited data for both training and validation. It reduces the risk of getting lucky or unlucky with a single small split. And because you're testing on different subsets, it gives a better sense of how the model generalizes.
That makes a lot of sense for small data sets. Maximizes data use, reduces overfitting risk, gives more reliable metrics. And I assume libraries like sklearn make this easy.
Oh yes, sklearn has tools like cross-fault score that handle the whole folding and averaging process for you. It's standard practice for smaller data sets.
Okay, great. So let's try to consolidate all this into a quick cheat sheet. When to use what?
Good idea.
Situation, large data set.
Train validation test split.
Situation, small data set. Use.
Cross-validation.
Yeah.
Scaffold. Almost always better.
Situation. You want the final model ready for deployment. Train on.
Train plus validation sets combined. Then test on the held-out test set.
Situation. You want to
Understand.
compare different models or feature ideas. Use.
Validation set, if using train Valtist or cross-validation result.
Situation. You need to tune hyperparameters. Use.
Validation set or cross-validation within your training process.
Situation. You need that final, unbiased performance estimate. Use.
The test set. Once. Only once.
Perfect. That really clarifies the purpose of each strategy.
Yeah, knowing when to apply each method is just critical for building models you can actually rely on.
So we've covered a lot. Logistic regression, SVMs, and this crucial art of splitting data using train validation test or cross-validation. Hopefully this deep dive has clarified things and maybe sparked some ideas.
The goal is moving from just knowing the terms to really understanding why and how you use these techniques.
Absolutely. So here's a challenge for you, the listener. Try this out. Grab a data set, maybe the classic Iris data set, or even better, something from your own work or area of interest.
Get your hands dirty.
Split it, say 7-0-1-5-1-5 into train, validation, and test. Train a simple model, maybe logistic regression to start. Evaluate it on the validation set. Try tuning a parameter or two based on that validation score. Then finally, do that one single evaluation run on the test set.
Actually, going through the steps makes a huge difference. You'll feel why each stage matters. And hey, if you want a more specific challenge, like building a basic fraud detector or predicting customer churn with sample data, let us know. We could even sketch out a custom scenario for you to try.
Great idea. That hands-on practice is invaluable. Okay, that's all for this deep dive. We really hope this look at logistic regression, SVMs, and data splitting has been helpful.
Hope it cleared things up and gave you practical tools.
Keep exploring, keep questioning, and join us next time as we continue to demystify the fascinating world of machine learning.